Those of you who are in here, excuse me, our face-to-face test was supposed to be done by today or tomorrow. And Jada, amongst other people, had some issues, so I'm pushing it off till at least Wednesday possible. So you now can do, in addition to the 11 a.m. tomorrow morning and the 7, I think it's 7 p.m. tomorrow night, you can also do a 7:45 a.m. on Wednesday. So if anybody wants to put in that slot, just send me an email. Let me know that's your plan, and I'll take care of it. And I'll remember to send an email to Portsmouth because one student's already taking it on Wednesday. Anybody have any questions before we get started? All right. Well, it looks like we got a pretty good number of students here. I have put the grades in. Anna probably saw her grade. The class average was not that high on the first test, so I don't want to talk too much about it because there's some people that haven't taken it. But the class average was not that high. I just want to tell you guys that I'm aware. I'd normally expect this on the first test, but not the second test, even though the second test is not necessarily all that super great either. But the way my class is designed, and I want it this way, is specifically even if you got a 12 on the first test and an 18 on the second test, the face-to-face test, that is, you still have another face-to-face test and you still have a face-to-face final exam, both of which are comprehensive. In principle, you can still very much get an A, and that means even if the numerical grade cannot work out to give you an A, I'm still on board with giving you an A if you earn it. And by earning it, I mean you have to pass a comprehensive test like at the level of 95, 96 or higher to get an A, or at the level of 85 or 86 to get a B, or at level of 75 or 76 to get a C, something like that. So that's just something I do every semester because really what matters is can you peak at the moment that you need to peak. That shows me, a little chutzpah and stuff like that. So that's what I try to shoot for. So don't worry if your grades are bad and it looks like it's impossible for you to pass. That's very much usually on the order of two or three students out of 24 will have something like that happen. But I usually only have one or two students fail every semester. Uh, at most, and usually those are ones that just stop showing up. So I doubt anybody necessarily has to fail, but I certainly say everybody still has a chance to get an A. So please do your best. Use this opportunity between now and your next face-to-face test and now and your final. Make sure you use this opportunity to learn how to do exactly those problems that you didn't completely understand on face-to-face test one, again on face-to-face test two as well. Use that opportunity to learn it. There's no optional sections in physics. When you go through chapters 1 through 9, for instance, uh, every bit of material that you covered in chapter 1 and chapter 2 and chapter 3 has a way of sneaking back up on you and is fair game. So I just want you guys to realize it's a completely comprehensive course. And if you think you can just sort of skip this one part you didn't understand, inevitably it's going to find a way to bite you in the rear. So make sure you ask me, you get help, or work with another student, work on Khan Academy, or use some AI to try to learn how to solve the problems, but learn how to solve the problems. We still have all the practice tests coming up, and if you're doing practice tests every test, then you're getting a really large amount of experience from solving physics problems. So just keep that up. Anybody have any questions before I get started? Because I need to jump right into chapter 9.
Yeah, I have a question, Professor. Were you saying that if we don't do good on a face-to-face test and on the final, let's say somebody gets a 90 or a 95, they get an A for the class? That's what that mean, or
Yeah, what I mean is above the halfway point. So the halfway point for the A is around the 95. So if you make a 95 or higher on the comprehensive final, for instance, and I don't have any reason to suspect you cheated or anything like that, not saying you personally, just a student in general, then there's a high probability that you're going to get an A, even if the grade doesn't work out to be an A
oh,
numerically.
okay. All right.
And I
Thank
do that for everybody. And I check literally. There's like three different calculations I do every time I do my final grades in 241, 242. Actually, I do it in all my classes, but I check all the different ways that I can get your grade to highest, and I give each of my students the highest of those three types of calculations.
you. Okay, thank you.
You're welcome. So please talk to me, guys. If y'all have some material you don't understand, you don't have some kind of physics problem you don't understand, or some topic, make sure you ask me for help on that. So I don't want to talk about specifics on the test right now. Like I said, I still got several people that haven't taken it, and as soon as they finish, then I'll be able to grade it. I don't grade except for the rare instance, like one student of mine took the test on Wednesday of last week, and I graded theirs immediately because I'd graded everybody else's. But normally I wait and grade the whole class together. So I'll wait for everybody to finish this test, which could be now Wednesday, and then I'll give you back your test, or I'll announce the test scores. I'll put the grades in, and I'll allow you to look at a key and that sort of stuff. All right. So last time we were talking, we had gotten through example 9.9, and now I'm going to do something equivalent to example 9.10. We're in the chapter on momentum, conservation of momentum, center of mass, kinetic energy being conserved, call it elastic collision, inelastic collisions, completely inelastic collisions, all that stuff we're going to talk about. So I thought I'd start off with an example, sort of like example 910. I've sort of changed it a little bit, but let's go ahead and share my iPad screen and see if you guys can follow what's going on here. And remember to ask me questions if you don't understand what I'm talking about. That's what I get paid the big bucks for, folks. All right, so I say consider the ballistic pendulum shown below. A bullet of mass lowercase m has an unknown muzzle velocity v sub m and immediately embeds into a large block of mass big M that is able to swing like a pendulum. If the block raises to a height h, use that height h, lowercase mass m, and uppercase mass big M to determine the muzzle velocity. So the way this problem is solved is we initially have a conservation of momentum problem with regards to the first two steps. So I like to write this like this and say this is conservation of momentum. And then from here to here, it's conservation of mechanical energy. Oh, that went off the rails really quickly. Conservation of mechanical energy. So that's the way we solve it. Again, the necessary requirement for momentum to be conserved is that the net external force acting on the system is zero. What we see here is a mass little m with a velocity vm getting ready to collide with a mass big M. Now, there's a huge force acting between little m and big M in this collision, but that's an internal force because our system is little m plus big M, the big mass and the little mass together. And the force is acting on them is a gravitational force in the downward direction on the bullet, but it's going to be in the air for like a split second, and you're not even going to, because it's moving so fast, you're not even going to see it deflect downward. So we can assume that the net force on the bullet is going to be zero. Similarly, there's a downward force, big mg, due to gravity on the block, but as you can tell, the two strings are going to keep that from falling down. So that's sort of like a normal force that cancels it out. Because of that, we can say the momentum is conserved. And the way we conserve momentum is the following. I'm going to say the initial momentum is just m times vm. After they collide, then the momentum is m plus big M times the new velocity they have, which I'm calling v2. I wrote the subscript 2 at it and make it a new looking thing like that, the Greek letter nu. I didn't make it look like that, but that's the key point. Now, from that, I can tell that the velocity of the block with the bullet embedded in it, v2, is actually equal to m over m plus big M times v muzzle velocity. So now I have the velocity of v2. Now I've done the conservation of momentum part. Now I'm going to do the conservation of energy part, and this is mechanical energy. So the conservation of mechanical energy says that UI plus KI plus work in is equal to U final plus K final plus work out plus E loss. Now, we're not taking into account anybody applying any forces or any springs being compressed or any friction forces and that sort of thing. So I'm immediately going to get rid of the E loss and the work out and the work in. Additionally, the potential energy initially is going to be zero. Basically, what I'm assuming is roughly half the thickness of that big block M. Uh, the height of the bullet is not going to change. It's basically half the height of that M. So that we might choose to call the zero potential energy for the little mass M to just be the midline right through the big mass, the mass big M. And we're going to say y equals zero for the bottom edge of the mass big M. So our initial momentum, our initial potential energy, excuse me, is going to be zero as well. But what I do have is one half. Oops, let me make sure I got everything else. Then at the end, after the bullet's been embedded in it and the block with the bullet embedded in it lifts up like that, that's going to come to a stop. So the kinetic energy there is zero. So I put that as zero. And now what I have is basically one half m plus m v2 squared is going to be equal to m plus m times g times h, where h is the new height. So, with that in mind, we can go ahead and, for instance, see that the masses cancel out, and I can go ahead and substitute my mass M2 in there. And what I'm going to have is one half of V2. So that V2 we just found was, where did we find that? Oh, yeah, that's right. V2 is equal to M over M plus M times VM. Now that has to be squared. Oops, hold on a second. I forgot. Oh, that's right. I did already get rid of the. Yeah, I already got rid of the mass, so that's okay in that case. Uh, so what I'm going to do now is square the M and square the VM. And then that, of course, is all equal to G times H. So I can go ahead and say VM squared is equal to 2 times G times H times M plus M over M. And in this case, they're both squared. Now I'm going to take the square root of both sides, and from that, I'm going to get the muzzle velocity is equal to M plus M over little m times the square root of 2GH. And that's it. That's the whole process. So now we've seen how we use conservation of momentum, specifically this part right here, to solve for the collision so we'll know what velocity the block with the embedded bullet in it, what velocity it takes off at, and then we use conservation of mechanical energy to set that equal to the kinetic energy afterwards, because the potential energy is going to be converted to kinetic energy, and then from that we can solve for the muzzle velocity. So now if you use this device to calculate a muzzle velocity, then all you have to do is use this one formula that I have here. Anybody have any questions on that? All right, so check out example 910 because this is just like it. Uh, and you might find that his explanation, along with this one or in lieu of this one, you might actually find that's pretty helpful. So just like example 910. So again, anybody have any questions on that? Does not look like you do, and I'm trying to check the chat right now, but okay, you got that. Now let me open up the chat window just to make sure I have that. Yep, no one typed anything. Okay, Let's move on to the next example, which is example 911. It says calculate the loss of kinetic energy of the two train car system from example 9.3. So remember, example 9.3 was I think it was a 10,000 kilogram car moving at 8 meters per second, runs into a stationary 10,000 kilogram train car that, again, is sitting still. However, they get stuck together, and then basically what leaves that collision is a mass of 20,000 kilograms with a new velocity v, and we worked it out and found out the new velocity, because of the mass being twice as big, was in fact half the original velocity. So if it was 8 meters per second before, the velocity afterwards is now 4 meters per second. So that was the example we're working. So what I want to show you is, in this case, they want to calculate the loss in kinetic energy. So let me show you what we had. We have a train car that has, and I'm just going to call it a mass big M. I'm not even going to worry about putting the numbers, because I'm going to work it out symbolically, and you'll see that we have a uh, a calculation for the change in kinetic energy. So this is V1, that's the initial velocity. Now there's also a second train car that has a mass big M, and then sometime later, so I just put an arrow and write time. Now, sometime later, what's going to happen is the two train cars will collide and get stuck together, and they're going to move off with a new velocity v2. So, what we know is that conservation of momentum gave us m v1 is equal to 2m v2. That's conservation of momentum, and therefore we see that v2 is actually v1 over 2. So that was what we were able to conclude about this. Now, what we want to do is calculate the initial kinetic energy, which the initial kinetic energy before the collision was 1 half mv1 squared. After the collision, the kinetic energy is 1 half. Now you've got 2m for the mass, and now you've got v1 over 2 for the new velocity. So that's the new kinetic energy. And you can probably see that the 2 in here is going to cancel out with the 2 down here, but we're still going to have 1 half times 1 half mv1 squared, like that. Notice, because we're squaring the v1 over 2, that becomes v1 squared over 4. So I broke that fraction into 1 half times 1 half, because 1 half times 1 half is still 1/4. Now I can do change in kinetic energy would be K final minus K initial. And obviously, what you get there is 1 half of 1 half mv1 squared minus 1 half mv1 squared, which tells you automatically that we have 1 half minus 1 half, so that's 1 half of k initial, because you can basically write it as 1 half times 1, or excuse me, I can write that as, no, I don't want to do it that way. I can write this as 1 half mv1 squared times 1 half minus 1, like that. And that's really where it came to. So what we see is the change in kinetic energy is a loss of 1 half of K initial. And that's really the answer that we're looking for. If you look at the answer in the book, they actually did it with numbers, and that's fine. It's just what I've done is, now for all cases where two objects of the same mass, has one of them moving initially and then runs into the other one, sticks to it, and then, of course, leaves with some common velocity. In all of those cases, since the two masses were identical, the loss in kinetic energy will be 1 half of the total kinetic energy. Any questions on that one? All right. So we've done that example. Now I want to get into collisions in 2 and 3 dimensions. And again, I want to remind you guys, I'm saying this over and over again. Just like you're supposed to know Newton's first law of motion and exactly which one is Newton's first law, Newton's second law of motion and which one second is the second law, and Newton's third law of motion and Kepler's first law of planetary motion, Kepler's second law of planetary motion, Kepler's third law of planetary motion. And by the end of the 2 semester sequence, you're going to have to know conservation of energy, conservation of linear momentum, conservation of angular momentum. You're also going to need to know Maxwell's equations, all sorts of crazy stuff like that. But every time we have a big topic like this that engulfs an entire chapter, you should memorize the fundamental statement of that thing. So the fundamental statement, for instance, in the past was Newton's first law. Another one was Newton's second law. Another one's Newton's third law. Later, we're going to have the first law of thermodynamics, the second law of thermodynamics, the zeroth law of thermodynamics, the third law of thermodynamics, all that good stuff. Well, here's another one. Under what conditions is linear momentum conserved? So I've taken the time to again write that here, but I want you guys to know that's something you should commit to memory. You should be able to answer at the drop of a hat. Under what conditions is linear momentum conserved? And by the time we get through I think it's chapter 11, you should know under what conditions is angular momentum conserved. Okay. You should also know under what conditions is energy conserved, what conditions is mechanical energy conserved, that sort of thing. All right. So now with collisions in 2 or 3 dimensions, we're going to work on that. Now, it may seem like I'm trying to study arbitrarily easy problems because what I'm going on is a mass ma that is initially moving with a velocity va runs into a mass mb that's sitting still. That sounds like a special case, and in some sense it is, but remember, we have the equations that tell us how various quantities in physics are related in one reference frame versus another. So when we actually solve projectile motion problems or let's say elementary particle collisions, that sort of thing, we can jump to a reference frame in which one of the particles is not moving. And therefore, we can always consider one particle not moving, and that's not a loss of generality. Similarly, we're allowed to choose our axis to point any way we want, our y-axis to point any way we want, and our z-axis to point any way we want. As long as we try to keep a right-handed coordinate system, we're not going to run into any problems with that. So it's often very useful for us to assume that the particle that's moving happens to be moving in the positive x direction. Uh, so that's what I've done here is I'm going on the assumption that one, the particle that is moving is m sub a and it has a velocity v sub a, and that v sub a is going in the positive x direction. And the particle m sub b that's going to be hit has a velocity of 0. And then after the collision, because it's 2 or 3 dimensions, the particle MA and the particle MB could leave at very different angles. So that's what I have here. If we assume that the summation of the forces is equal to 0, then the summation of forces, which is equal to dp dt, remember that's Newton's second law of motion. This part right here, since this is 0, that means this is 0. And that means in order for a derivative to be equal to 0, then, and this should be a 0 vector specifically speaking, in order for a derivative to be equal to 0, the thing you're taking a derivative of must be a constant. So P is a constant, and it happens to be a vector. That's why I put a vector symbol over it. Okay? So if I assume, as my drawing is here, that MA is moving in the positive x direction, and we got MB sitting at the origin, sometime later you see the two are colliding. That's supposed to be like a like a sound popping out or whatever, and then time elapsed again, and what's happening now is MA is taking off at an angle theta A prime with a velocity V A prime, and MB is taking off with a velocity VB prime at an angle theta B prime. Okay? So conservation of momentum in the x direction gives me MAVA is equal to MAVA prime cosine theta A prime plus MBVB prime cosine theta B prime. Does everybody see how the cosine gives us the x component of the momentum? Anybody have any questions on that part? Okay. Also, we have conservation of momentum in the y direction. Of course, the particle was only moving in the x direction, so the initial momentum in in the y direction is zero. So all we get in this case is ma va prime sine theta a prime plus mb, excuse me, vb prime sine theta b prime. Now, that's two equations, and therefore the fundamental theorem of algebra tells us if we have two independent equations, then we can have up to two unknowns. So if there's two unknowns, you can solve it with this, if assuming again that it meets the criteria for conservation of momentum. However, sometimes we'll give you a collision problem where there's three unknowns, and the only way you can solve that is if we give you a third equation or we tell you that the collision is elastic. Remember, elastic means kinetic energy is conserved. Kinetic energy is 1/2 mv squared, but as you know, all the terms are going to have 1/2 in front of it. So I went ahead and multiplied through by 2 to get rid of the 1/2. So there was a 1/2 here and a 1/2 here and a 1/2 here, but all I did was multiply by 2, so that got rid of it. So now the conservation of kinetic energy, which is necessary or which is true in an elastic collision, tells us that ma va squared is equal to ma va prime squared plus mb vb prime squared. Does everybody follow that? Anybody have any questions on any of that? Okay, so I'm getting ready to show you a technique to use these at least two of these equations to actually solve the system of equations. And it's very important, as I wrote down here in blue, it's very important that you memorize this technique because this technique is not just a handy way that Giancoli is solving this particular problem. It turns out that this is sort of the one very efficient way of solving this so that you can consistently get the right answers with a with a two body two-dimensional collision. Okay. So not only do you have to memorize those three equations, px, py, and kinetic energy, what I call it equations one, two, and three, you also have to now memorize this method that I'm getting ready to show you. Okay. So anybody have any questions on that before I move on? All right. How do we go about solving this? Well, the trick is in equation one, we want to get all the m sub a's on the left and all the m sub b's on the right. In equation two, we want to do the same thing, get all the m sub a's on the left and all the m sub b's on the right. And the way we're going to do that is we're going to subtract the m sub a terms and make sure they move over to the left hand side, and then we're going to square both sides. Okay, so that's the two steps. Get all the A's on the left, all the B's on the right, and then square. Get all the A's on the left, get all the B's on the right, and then square. So with that, I now have, was I writing in purple? I'll go back to purple then. So now I'm going to say MAVA minus MAVA prime, and this was the X, so that's cosine theta A prime, is equal to MB VB prime cosine theta B prime. I'm going to call that equation, I think I did number one there. Yeah, I'll call this equation one prime. Not quite finished yet, but we're going to do some stuff with it. Now I'm going to square both sides. Okay, now this one's a little bit more difficult because by squaring it, it's a binomial, so I have to, do the FOIL method basically. But we know from experience that the FOIL method will give us the following results. M sub a squared v sub a squared minus 2 m sub a squared v sub a prime cosine theta a prime. And then the square of the last term, which would be m sub a squared v sub a prime squared cosine squared theta sub a prime. That's all equal to a very simple mb squared vb prime squared cosine squared theta b prime. So let's call this one double prime. Okay. So that's what happens when I squared equation one. Now I'm going to take equation two and square it after I get all the stuff on the same side. So equation two prime is going to be written basically as m sub a v sub a prime sine theta a prime is equal to m sub b v sub b prime, times sine theta b prime. Now I'm going to square both sides. Now this one's not a binomial, so that actually makes it a little easier to square it. But what I end up getting is, and I'm going to write it over here for a reason that'll become obvious in a second, but ma squared va prime squared sine squared theta a prime is equal to mb squared vb prime squared sine squared theta b prime. This is 2 double prime. Okay. Now what we're going to do is, oops, add equations 1 double prime and 2 double prime. So we're adding them. And when we do, we're going to get some fairly nice looking stuff. We'll get m sub a squared v sub a squared minus 2m sub a squared v sub a v sub a prime cosine theta a prime plus m sub a squared v sub a prime squared. Now remember the ma va prime squared, those are both like terms, so I can go ahead and add them together, and what I have left is sine squared dot 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 plus cosine squared dot dot dot. The same thing happens on the right hand side, and I end up getting m sub b squared v sub b prime squared sine squared dot 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 plus cosine squared dot dot dot. So that's the home run that makes this method so useful. Is I've gotten rid of instances of trig functions of theta. There's only one trig function of theta left, and that's the cosine of theta a prime. Uh, by doing that, that's made this equation a lot easier to deal with. So I'll go ahead and rewrite my final equation. That is ma squared va squared minus 2ma squared va prime cosine theta a prime plus ma squared va prime squared equals mb squared vb prime squared, and that's it. So this is the equation that I was wanting you guys to get. And the main thing is, as I told you, you need to commit this method to memory. I'm not going to give you that equation. If I give you a two-dimensional collision problem, you're going to have to work something like this out. And I tell you, you can, in principle, just look for a way to solve the system. But if you don't choose this way, it's going to be a lot harder, and there's a high probability that you won't be able to get it solved. So you just have to commit that to memory. Anybody have any questions on that? All right, so that was a really big derivation, if you will, and hopefully you understand exactly why we did what we did and why it worked out and all that good stuff. We can go ahead and work example 912 now. I'm going to go ahead and flip to another page to work this. So let's say example 912. Example 912 again, if you have your book, this would be helpful for you to read. I'm going to read it to you, but it would be helpful to have your electronic version out so you can read it. Billiard ball collision in two dimensions. So a billiard ball A moving with speed VA equals 3.0 meters per second in the positive X direction, see figure 919, strikes an equal mass ball B initially at rest. The two balls are observed to move off at 45-degree angles to the x-axis, ball A above the x-axis and ball B below. That is, theta A prime is equal to 45 degrees and theta B prime is equal to negative 45 degrees. What are the speeds of the two balls after collision? So they didn't tell us anything in this collision about the collision being elastic or anything like that. So all we know is that we can go on the assumption that momentum is going to be conserved because we're talking about pool balls and the total force on them would be basically gravity versus the normal force, and those two cancel each other out. All the other forces are going to be internal forces. So conservation of momentum is definitely a fair assessment of what to do. Now, in this case, this one's so straightforward, we don't necessarily have to use that big equation that I just found, but we can. So that's something else that's kind of helpful. And I'll show you how to use that big equation as well as the kinetic energy being conserved equation. So first off, remember our conservation of momentum in the x direction, P sub x, gave us, in this case, all the masses are the same, so we're ultimately going to get rid of them, but I'll draw them here for a second. I've got MA VA is equal to MA VA prime cosine. Now, A was the one that went above the x-axis, so this will be positive 45 degrees. And I'm assuming it has three sig figs, even though they only gave me two. And V sub A is equal to 3.00 meters per second. Again, they gave us 3.0, but I'm calling that 3.00 just so I can have three sig figs. So I've got that quantity. VA prime is one we want to know. And then we also have plus MB VB prime cosine negative 45.0 degrees. Okay, so that's conservation of momentum, but using MA equals MB is just plain M, we can divide both sides by M, and what we're left with now is just VA, which we know is equal to VA prime cosine of 45. I think y'all know that's root 2 over 2 plus VB prime times the cosine of negative 45 degrees. And cosine, remember, is what we call an even function. So the cosine of negative 45 is the same as the cosine of 45. So that's also the square root of 2 over 2 for that particular case. And automatically we can start to see that since we know VA, VB and VA must add to give you, or VB prime and VB A prime must add to give you the VA once multiplied by the same number. So we're pretty close on having that. Now I also have conservation of momentum in the Y direction. And remember that is 0 is equal to MA VA prime sine 45.0 plus MB VB prime sine negative 45.0 degrees. Now, in this case, again, we can divide through by the masses. And what we get instead is 0 is equal to VA prime square root 2 over 2. Sine of negative 45 is the negative of the sine of 45, so that's going to be minus VB prime square root 2 over 2. And from this equation, we can tell immediately that VA prime must be equal to VB prime. Now I can use that with this equation, which I'm calling 1, this equation, which I'm calling 2, and this equation, which I'm calling 3. So plugging 3 into 1, we get the following. And I'm also going to go ahead and plug in VA being 3 meters per second. So I got 3.00 meters per second is equal to VA prime times the square root of 2 over 2 plus the square root of 2 over 2. Because remember, they're both the same. So I just basically removed VB prime and replaced it with a VA prime. So now I can add these numbers and I get 2 times the square root of 2 over 2. So that's just VA prime times 2 square root 2 over 2, which gives me that VA prime, which is also equal to VB prime, is actually equal to 3.00 meters per second divided by the square root of 2. And I thought I got my calculator, but I seem to have forgotten to bring it. But I have extra, so hopefully this one will be charged. This does not seem to be the one that's charged, so that's not helpful at all. Okay, well, that's easy enough. I can do it with my phone. And with my phone, I get 3 meters per second. And now I'm going to divide that by the square root of 2. And that gives me 2.121 meters per second with one extra sig fig. And that's VA prime. And that's also equal to VB prime. Any questions on that? And looking at it, they've got VB prime equals VA prime, so they got the same conclusion I did there. And they're calling this 2.1, but I use 3 sig figs instead of 2, so I call it 2.12. Any questions on that? All right, let's look at another example. This one's going to be example 913. Now, remember, I told you the way that we handled the x momentum and the y momentum by doing that square thing, getting all the a's on one side and the b's on the other side, then squaring it, then add those two equations, and that gave us something really simple. But with the kinetic energy part, we can also always solve for VA prime in terms of VA and VB prime, so that that can eliminate one of the variables. So that's the big trick of using this. In example 913, it says proton-proton collision. A proton traveling at a speed of 8.2 times 10 to the fifth meters per second collides elastically with a stationary proton and a hydrogen target, as in figure 918. One of the protons is observed to be scattered at an angle of 60 degrees, and at what angle will the second proton be observed, and what will be the velocities of the two protons after collision? So in this case, I've got VA is equal to 8.2 times 10 to the fifth meters per second. Of course, VB is just 0, but that we already made the assumption of anyways. MA is equal to MB, is equal to m, and we're going to say that's basically a proton, so that's roughly 1.01 u or something like that, but it's not really going to matter. And we're going to say theta a prime equals 60 degrees, or theta b prime equals 60 degrees, because we really can't tell one proton from the other, right? We're not necessarily going to know which one's which. But that being said, we can start off with our conservation of momentum again. So P sub x, using the fact that the masses are equal, is going to give us VA is equal to VA prime cosine. Now, in this case, we can choose to make theta A prime 60 degrees, or we can make theta B prime 60 degrees and then solve for whichever one we didn't make it. But right now, I'm just going to put the symbols in. So theta A prime plus VB prime cosine theta B prime. So let's go ahead and call this equation 1. That's conservation of momentum now that I've gotten rid of the mass. I also have conservation of momentum in the y direction. Again, getting rid of the mass. That's going to give me 0 is equal to VA prime sine theta A prime plus VB prime sine theta B prime. And that's going to be equation 2. Now, the conservation of kinetic energy, which is from the elasticness of the collision, because of that, we can say the kinetic energy, again, remember the masses are all the same, and I've already gotten rid of the factor of 1/2. So all we have left now is VA squared is equal to VA prime squared plus VB prime squared, like that, and that's going to be equation 3. So, like we learned before, we're going to do the exact same thing. I'm going to take equation 1 and get all the A's on one side and the B's on the other side and then square it. And equation 2, I'm going to do the same thing. So, first off, with equation 1, I'm going to say VA squared minus 2VA VA prime cosine theta A prime plus VA prime squared cosine squared theta A prime is equal to VB prime squared cosine squared theta B prime. So that's now going to be 1 prime. And now 2 prime is going to be basically VA prime squared sine squared theta A prime and VB prime squared sine squared theta B prime. And now I add 1 prime and 2 prime. And when I add them, I can see that I get VA squared minus 2VA VA prime cosine theta A prime plus VA prime squared times, remember that's going to be sine squared plus cosine squared is just equal to 1. And that's equal to VB prime squared, again, times sine squared plus cosine squared. So I'm going to go ahead and call this equation 4 because that comes in handy. Now that we have that, we can go ahead and make some use of anything. For instance, we have let's see what we can get rid of. We have a VA squared minus 2VA, VA prime, VB prime. That looks good. Uh, oh, we can take equation 3, and with that, we can go ahead and solve for VB prime, for instance. So VB prime squared is going to be equal to VA squared minus VA prime squared, like that. And I'm going to call this 3 prime. And I can plug 3 prime into equation 4. So plug 3 prime into 4, we get VA squared minus 2VA VA prime cosine theta A prime plus, remember what we're doing, we're taking and replacing the VB prime so that I can only have VA in the equation. That'll be super helpful. So it'll be plus VA prime squared is equal to VA squared minus VA prime squared. So the beauty of that is this VA squared cancels out with this VA squared, and in fact, what we can get is 2VA VA prime cosine theta A prime. That's what happens to that middle term when I pull it to the right hand side. And then I pull this VA prime to the left hand side, and that's going to give me 2VA prime squared. So I have 2VA prime squared is equal to 2VA VA prime cosine theta A. But we can see that clearly one of these VA primes will cancel out, and we get 2VA cosine theta A prime is equal to just 2VA prime. Now we can see that the 2 cancels out, and we have finally VA prime is actually equal to VA cosine theta A prime. So now I can plug in 8.2 times 10 to the fifth meters per second. And at this point, I might wish to assume the angle for theta A prime is the 60 degrees. So I'll say if theta A prime is equal to positive 60 degrees, then we get this, which is cosine 60 degrees. Again, using my phone as a calculator, 8.2 10 to the fifth times cosine 60, and cosine is 0.5. So this gives me 4.10 times 10 to the fifth meters per second is VA prime. And now we can plug that in. We have VA prime is equal to 4.10 times 10 to the fifth meters per second. We can plug that in our description for B prime. So, for instance, equation 3 prime gets us the following. VB prime squared is equal to VA squared, which is 8.2 times 10 to the fifth meters per second squared, minus VA prime, which is 4.10 times 10 to the fifth meters per second squared. And that gives me 8.2 times 10 to the fifth, enter, square it, and then 4.1 10 to the fifth, enter, square it. So I'm going to take the 8.2 squared minus the 4.1 squared, and that's going to give me 5.04 times 10 to the 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 times 10 to the 11th. And that's meters squared per second squared. So I can finally say that VP prime is going to be the square root of that. And that gives me 7.10 times 10 to the fifth. meters per second. Uh, that gives me my new velocity VB prime, and we can now go about figuring out what exactly is theta B prime when we assumed, because we already assumed that theta A prime was 60 degrees. So what must be theta B prime? Well, we can take equation 2 prime. I should write this way. So 2 prime implies we got VA prime squared times sine squared theta A prime is equal to VB prime squared sine squared theta B prime. So we can plug all this in, and in so doing, I'm going to have the theta A prime is 60 degrees. The theta B prime is what we're going to try to find. And I'll just write down the answer here. I think y'all can figure out how to do it at this point. So theta B prime, I think you're going to discover turns out to be uh, the negative of the inverse sine of zero point 0.5, which gives us negative 30 degrees. And that's it. Anybody have any questions on that? So that was a lot of work, but notice it was something that's somewhat doable. You just have to understand the trick, and the trick is that one, you're going to get all the MAs and on the left and all the MBs on the right. Then you're going to square it. Then you're going to add those, and then you're going to use the kinetic energy, the elasticity condition, to eliminate one of the unknown squared velocities. Once you do that, then you can, basically solve any of the 2 and 3 dimensional problems that you could. Anybody have any questions on that? All right, so far as algebra goes, this and chapter 26 is about the hardest, nasty algebra you'll ever have to do in the 241, 242 sequence. So it's just something you just got to live with and figure out. I've given you the technique that you're going to use to solve the systems, and you got to commit that to memory to some extent. But other than that, you should be good to go. Anybody have any questions? All right, so we've solved all the collision type problems that we need to solve. Now, what I'm going to go into teaching you is the center of mass. So, the center of mass is defined to be, let's stop sharing for just a second. So the center of mass of an object is basically the point within the object, and it's not necessarily physically in the body of the object. You've probably seen some demo things and toys for sale where they acted kind of weird, and the reason they acted weird was that their center of mass wasn't within their body. But the main thing is the center of mass exists, and it's the one point that all the object acts as if all of its mass is located at that one point. So, for instance, if you knew where the center of mass of this pin is, then you could immediately stop gravity from pulling it down by putting a object immediately in its path, and that would hold it up. So when I did that, I've evidently figured out that the center of mass is along this vertical line right through here. Now if I rotate it, now I can find out it's through this vertical line as well. So I've now located the center of mass to be right inside the center of this pin. So it's halfway from left and right and halfway from top and bottom. But we already knew that just from symmetry. It looks like it's pretty much it. Well, it's actually a little bit off. There's a flat spot right here, so that makes it a little different. But if it was cylindrical, it definitely would be along that. So I did manage to figure out where the center of mass is there, but I didn't figure out where it is left and right. But actually, I did because I was holding it up. So that means the center of mass is also in this plane right here. So not only is it halfway from the front to the back and halfway from the top to the bottom, it's also not exactly halfway because notice this end has a little less weight and this end is rounded. So it's along this line somewhere right below where I can balance it. And that looks like right about there. Okay. So that's what the center of mass is. Now, if you pretended this was like instead of it being a continuous body, you might say, okay, well, there's a slice of pencil right here, and then there's another slice next to it, and another slice next to it, and another. You could divide it up in little slices, and then what you'd see is if you pretend the center of mass is right here at the origin, all you have to do to figure out whether it really is the center of mass is you go to the left some distance and figure out the mass of that little slice and see how much of a torque, which we haven't learned about torque yet, but see how much of a torque it causes to rotate it this way. And then I go over to the next one that's going to cause a different amount of torque to rotate it this way, and then the next one, the next one, the next one. And then I do the same thing on the other side. And all I have to do is set it up so that that rotation is zero. Well, that turns out in order to do that, I'm going to have to need the distance from the origin to the first slice and then times the mass. And technically, I'd have to multiply that by g to get the force, but it's going to be a common factor of g everywhere. So, guess what? It turns out that for the center of mass, there's some formulas that we're going to use, and I think they make perfect sense, and your book goes through explaining them, and that's sort of what I was just doing there, was trying to help you understand it. So let me go ahead and share my screen again, and now I'll give you the equations. So when we're looking for the center of mass in the along the x-axis, then that's called x sub cm. So x cm is equal to m1 x1. So again, remember that's the distance from the origin over to m1, and then multiply it by m1, because obviously if you're really going over a distance here, that the larger that distance is, the more likely it is to rotate this. And two, the larger that mass is, the more likely it is to rotate that. So both of these quantities, m and x, tend to rotate it. Now I'm going to do the next mass, which is m2x2 plus dot 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 on up to mn times xn. Now that takes into account all n of the particles. But I need this to have units of x. So if x is in meters, I need it to have meters. If x is in centimeters, I need it to have units of centimeters. But I've got a mass on top times centimeters, or a mass on top times meters. So I've got to divide it by a mass to get rid of it. And it doesn't make any sense to divide by m1 or divide by m2 or divide by mn. But what does make sense is divide by the sum of the masses, m1 plus m2 plus dot 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 plus mn. So that's the formula for the center of the mass. It's the summation from I equals 1 to n of m sub I x sub I over the summation from I equals 1 to n of m sub I. Similarly, y center of mass would equal the summation of m sub I y sub I from I equals 1 to n over the summation from I equals 1 to n of m sub I. So these are your equations when you have discrete parts of things. So any collection of objects, like for instance, if you happen to have a rectangular tray that's a uniform tray, then you automatically know the center of mass of the uniform tray, which is shaped more or less like a rectangle. If you drew a line from this corner to this corner, and then another line from this corner to this corner, where those two lines intersected would be the geometric center. And since this is a uniform, I'm pretending it's a tray, even though it's really a piece of paper. When I actually did this with the uniform tray, the center of mass would be right in the geometric center, right? So if I wanted to put other things on it, then I just managed to calculate what the X center of mass is and what the Y center of mass is, and then my finger would go exactly under that X or X comma Y coordinate, and then I could balance it no matter how many plates I had on it or cups of different sizes and things like that. So that's the way we go about calculating the center of mass. If, however, if we need to break up a continuous body, what we can do is pretend, even though we know matter is discrete, it's made up of atoms, and atoms are discrete little entities, but those atoms are so small compared to regular dimensions that we can sort of pretend like it's going to be continuous, in which case the x center of mass is equal to the integral of x dm over the integral of dm, and the y center of mass is equal to the integral of y dm divided by, whoa, I forgot I'd used that really big version of my eraser. So y dm over the integral dm. So these are the equations when you're doing discrete objects, and I'll show you examples of both, for instance. Let's talk about, for instance, the center of the Earth Moon system. So, where is the center of mass of the Earth Moon system? Okay, I'm going to draw a coordinate system to help us out here. So here's my x-axis, there's my y-axis. I'm going to say the Earth is right here. So this is the mass of the Earth, and the mass of the Earth is 5.97 times 10 to the 24 kilograms. And then a great distance away, I have a mass of the moon, and that object has a mass moon equal to 7.35 times 10 to the 22 kilograms. And I happen to know that the distance r away is 3.84 times 10 to the 8th meters per second. I think that's the numbers off the top of my head, but it's close enough either way. Okay. So I have the center of mass of the Earth right along the x-axis, the center of mass of the Moon right along the x-axis, and I'm assuming that they're perfect spheres and they're spherically symmetric. That's not completely true, but it's pretty close. And what I want to calculate is the x center of mass. So the way I do that is as follows. So XCM is equal to the mass of the Earth, which is 5.97 times 10 to the 24 kilograms, times its position, which is 0, plus the mass of the Moon, which is 7.35 times 10 to the 22 kilograms, and its x position is 3.84 times 10 to the 8th. I don't know why I wrote meters per second there. It's meters, everybody. Please correct that. I actually do know why. Uh, what I use to help myself remember how far the moon is because it's just slightly bigger than a light second. So 3.0 times 10 to the 8th meters per second is what I was thinking. So I wrote meters per second instead of meters. But that's the way that works right there. So now I have m1 x1 times m2 x2, and now I have to divide by the sum of the two masses, which is 5.97 times 10 to the 24 kilograms plus 7.35 times 10 to the 22nd kilograms. So we can calculate this. In this case, I'm going to take 3.84 times 10 to the 8th. Notice I got 0 on the other one. I'm multiplying that by 7.35 times 10 to the 22. And that gives me 2.82 times 10 to the 31. And that's kilograms times meters. And then all that is divided by, I got to take 5 point, sorry about that, 5.97 times 10 to the 24 plus 7 point, oops, crap, screwed that up. Not used to using my calculator, my phone as a calculator. 5.97 times 10 to the 24th, enter. 7.35 10 to the 22, enter. Now I'm adding those two, and that gives me 6.04 times 10 to the 24th kilograms. Now I say 2.82 times 10 to the 31st. And this gives me 4.67. Actually, I just shouldn't underline that. 4.67 times 10 to the 1, 2, 3, 4, 5, 6 meters is the center of mass. Now, if you looked up the radius of the Earth, you'd find that that happens to be just inside of the Earth. So it's roughly, I always say it's about 7/8 of the way out. So that's the center of mass of the Earth Moon system. And when you see a drawing of an elliptical orbit for the Earth, it's that point on the Earth Moon system that's making that elliptical path. The actual center of the Earth is wobbling on each side of it, and this moon is going way around it like that. So that's a typical center of mass calculation. Anybody have any questions on that? Okay. Your book does some pretty nice examples of center of mass calculations, like example 914. These are all really simple. I'm going to calculate the center of mass of something on the integral side because I think these discrete ones are pretty simple. And there's plenty of videos. For instance, there's a great video of me using my understanding of a framing square to actually calculate the center of mass of the framing square. And that actually allows you to figure out, like, hey, if you hang a framing square from a hole in it, what's the angle that it's going to sit at? Because what happens is the center of mass will be directly below the contact point, namely wherever you're holding it up by, like a hole in it. The center of mass will be along that vertical line right through that spot, and that sets the framing square, which is literally just a piece of metal shaped like that. But anyways, that's a good thing for you to look at. You can look at it in my YouTube channel. So just do a search for framing square or just the word framing, and that should help you. But let's look at some continuous bodies that we're going to try to calculate center of mass for. So, for instance, let's say we have a x-axis and a y-axis, and what I'm going to do is imagine a triangle, and the height of the triangle is x, and the width of the triangle is w. And this is what we call a homogeneous lamina. That's what you'll learn about in calculus. But basically, it means it's a two-dimensional flat plate, basically. And The fact that it's homogeneous means that if I cut out a 1 cubic centimeter or 1 cubic millimeter section of it, and I cut out another 1 cubic millimeter section of it, no matter where I get it from, it will always have the exact same mass. So that's sort of what we're talking about here. Now, what I'm going to do is remember that x cm is equal to the integral of x dm over the integral dm. So first off, the result, I can tell you that if you start from the narrow vertex of a triangle and head towards the wide part, then it's always going to be 2/3 of the way to the wide part. So I suspect the center of mass for the x in this case would be 2/3 w. And the center of mass for the Y, I would say, is 1/3 H because I have to start at the top and come down 2/3 of the way. So I'm thinking it's 1/3 H in the Y and 2/3 W in the X is the center of mass. But how we go about calculating that? Well, the thing is, if I'm going to take the integral of x dm, I got to make sure my differential mass element does not have a significant difference in the x from one side to the other. So what I'm going to do is imagine a little piece of mass right here, and this dimension is dx. Now, the equation here for this part is y is equal to h over mx. That's the equation for that y. So the height of it is y equals h over m times the particular x that we're doing. So that's the height. So if I go to calculate the integral of x dm, then I need to know what dm is, and the dm's that we use are dm is equal to lambda times dl, or it's equal to sigma times the differential area, or it's equal to rho times the differential volume. Okay, that's the choices. In this case, it's a two-dimensional thing, so I'm going to say sigma is a constant, and specifically, I'm going to say this thing has a total mass m. That means that m, or sigma, should be m over the area, which is 1/2 h times w. So that's what sigma is supposed to be. Now I can use dm is equal to sigma dA, and doing that, I'm going to say I've got the x value of the coordinate right here, and then my dm is going to be sigma dx. Now, I need to actually figure out, well, actually, I only got 2 minutes. I'm not going to be able to finish this. I tell you what, we'll finish this next time, and because I only got 2 minutes, and that's really not enough to do it justice. You might want to go ahead and look at the examples that I have in last week's module as well as the new week's module. You guys are free to go. I'll call it at this point, and keep an eye on your email. I might send you an email and ask you to watch some videos, and I'll expect you to have watched them before you come to class next time. So go ahead and do that. Feel free to, oh, well, for starters, make sure you chat me your first and last name if you haven't done so already. But I'll wait here for the last person to leave in case anybody has any questions. But you're free to go. Thanks for coming, everybody.